When we watched our Big Bang Theory video just a few minutes ago, Sheldon defined the Doppler effect as the apparent change in frequency, not the real change in frequency, because once a wave has been made, the frequency of the wave never changes, but rather the apparent change in frequency, what it seems to be rather than what it really is. The apparent change in frequency of a wave, usually that wave would be sound, not always, but usually sound, due to the relative motion of the source and the observer. So if you think back to his definition, which is exactly this, it makes some sense. Okay, when the fire truck, which was in the second video that we watched, the third video that we watched, is moving towards us, it appears as if the frequency of the siren is higher pitched than it really is. When that fire truck was going by us and going away from us, it appeared as if the frequency of the sound was a lower pitch. The apparent change in frequency of a wave, in that case sound, due to the relative motion of the fire truck and the camera on the side of the road, due to the relative motion of the source of the sound, or whatever wave it is, and the observer. Now, why does this happen? Why does the Doppler effect happen? Well, let's start with a wave here that is, we'll say, the source. Okay, the source of the wave. You know what? Let's call it the fire truck. We'll call it F. That fire truck produces a sound. It produces a spherical sound, or a sound wave, a spherical sound wave that goes out in all directions. Okay, we're going to draw it in 2 dimensions, so you're going to see that wave going out like this as a circle. Now, if that fire truck is at rest, then that spherical wave keeps being produced. It ends up looking like this. We have a series of crests that are, for the most part, evenly spaced, because it's a uniform frequency, right? Does that make sense? If the fire truck is at rest, that's the way the wave goes. Now, if I'm standing over here as an observer, what do I hear? As this wave goes by me, I hear crest. As this wave goes by me, crest. As this wave goes by me, crest. So what do I hear? Crest, 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 crest. That's the sound that I hear. Wave, 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 wave. Now, if the fire truck is moving towards the observer, is moving towards the X, watch what happens. This wave, let's label these waves 1, 2, 3, and 4. Wave number 1 is going to be in the same place, because wave number 1 was produced way back when the fire truck was way back there. But wave number 2 and wave number 3 and wave number 4 won't be in the same place, because you understand what's happening here. The fire truck is moving. As the fire truck moves, the waves kind of get scrunched together. And you notice this first wave that was produced by the fire truck right here is a circle right around that fire truck. But the wave that was produced a few minutes ago is a circle, but not centered around the fire truck, not centered around this spot right here, because the fire truck is trying to catch up to that wave. The fire truck is trying to catch up to this wave. It's trying to catch up to this wave, all of these waves that were made a few minutes ago. So if I'm standing right here, I heard when the fire truck was at rest, I heard wave, 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 wave. What do I hear now? Wave, 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 wave. I hear them in quicker progression because the waves, the crests of the waves, are scrunched together more. That gives me a higher pitch. When I hear more waves per second, I perceive a higher frequency. Now, if I happen to be standing over here on the other side, as the fire truck is going away from me, what do I hear? I did hear wave, 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 wave. When it was coming towards me, I heard wave, 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 because the waves are kind of scrunched together. As it's going away from me, what do I hear? Wave, wave, wave. Not as quick, right? Not as quick progression, because the waves are spread apart behind the source as it's moving away. Does that make sense? So you hear a higher pitch. Doesn't mean the frequency is really higher, but we perceive it as higher because of the scrunching of the waves as it's coming towards us, but we perceive a lower pitch when it's going away from us because of the spreading out of those waves. Rachel, question?
So when do you hear the actual?
When do you hear the actual noise it makes? When the fire truck is at rest. Okay, when the fire truck is at rest, then the waves don't get scrunched together or spread apart, and the observer over here is just going to hear the actual frequency that the fire truck is actually producing. Now, we get a similar effect if the observer is moving as well. You can imagine if the observer right here is moving towards the fire truck, then he's going to hear, he or she is going to hear more waves per second because he's going towards them, right? If he's going away from the source, then you're going to hear a lower pitch, even though the actual frequency of the sound doesn't change. So when they're moving towards each other, regardless of which one's moving, we hear a higher pitch. When they're moving away from each other, regardless of which one's moving, we hear a lower pitch that actually exists. All right, I'm going to give you an equation that's going to mathematically describe this phenomenon of the Doppler effect. It's kind of an ugly looking equation, especially for a last equation of the year. It says FD is equal to VW over VW plus or minus VS times FS. What does all that stuff mean? Well, FD stands for, anyone want to take a stab at it? Somebody said it? The Doppler frequency. The Doppler frequency is the apparent frequency. This is what we perceive. It's not the actual frequency of the sound or whatever wave it is. It's the apparent frequency. And the units for that would be hertz. FS is going to stand for the frequency of the source, or the source frequency, which is going to be the actual frequency. Not the frequency that you heard in the video when the fire truck is coming towards you or when it was going away from you, but rather the frequency of the siren that you would have heard if the fire truck was at rest and if you were at rest, the actual frequency. It's also going to be measured in hertz. Now, what do you think V stands for? Forget about W or S, just V. Speed, yeah. The speed is going to matter, right? If it's the apparent change in frequency due to the relative motion between the source and the observer, then it stands to reason that the speed is going to matter. How fast the fire truck is moving, how fast the source or the observer is moving. Now, what do you think VW stands for? No. VW stands for the speed of the wave. Now be careful with that because typically the wave here is going to be sound. It doesn't have to be. Okay, we sometimes use the Doppler effect in the analysis of astronomical phenomena. Okay, have you guys ever heard of redshift or blue shift in the context of astronomy? Redshift occurs when whatever is producing the light is going away from us, is receding. And the reason that occurs is because, the reason we see red is because red light is the lowest frequency light. So we perceive the light as a lower frequency than it really is when whatever's producing it is going away from us. Just like the frequency of the fire siren sounded lower when the fire truck was moving away from us. Now, a blue shift occurs when the frequency of the light is higher than it really is. We perceive it as higher than it really is. Blue frequency is high frequency light. Red is low, blue is high. So when it's coming towards us, we perceive a higher frequency of light, therefore we call it a blue shift. Usually we talk about this in the context of sound, but it can really be in the context of any wave. It's just 9 times out of 10 going to be sound waves that we're analyzing here. So we're not going to call this the speed of the sound. We're going to call this the speed of the wave, the speed of the wave. And that's going to be measured in meters per second. That usually is sound, but not always. Now, please don't get this mixed up with VS. One of the most common mistakes that people make with this is to call VS the speed of sound. But it isn't the speed of sound, because VW would be the speed of sound if we're dealing with sound. VS would be the speed of the object or the source, yeah, the speed of the source. So in the example that we gave you in the video, it would be the fire truck. Or it would be the van in the other video that we watched. Whatever it is that's causing the sound. Now, finally, and this is the trickiest part of it, this whole plus or minus thing. It's not both. It's never both. It's plus sometimes, and it's minus sometimes. I want you to think about this now. If you're like me, you have trouble remembering little things. You have to figure out little things. Okay, I'm much better off if I understand something and figure it out rather than try to remember. Remember I was telling you about diffraction? And I said the only way that I remember that low frequency waves diffract more is the story that I told you guys about listening to AM radio versus FM radio, right? AM radio I could hear at the bottom of the hill, FM I couldn't. Therefore, I remember that low frequency waves diffract more than high frequency waves. It's the only way I remember that is a way of remembering it. Same deal here. Yeah, I'll never remember when it's positive, when it's negative, so I have to figure it out each time. If I add VW and VS versus subtract them, if I add them together, make it a plus, then what do I get on the bottom? A smaller number or a bigger number? Bigger. If I add these two numbers together, I get a bigger number. So if I put a plus in there, it becomes a bigger number on the bottom. If it becomes a bigger number on the bottom, FD becomes smaller. When is FD, the Doppler frequency, supposed to be smaller? When it's going away, right? Picture the fire truck. When it was going away from us, we heard a lower frequency than actually existed. So we're going to say it's plus, it's positive when it's moving away. Ask me that 5 minutes ago and give me 0 seconds to think about it. I can't tell you the answer. Okay, ask me that 5 minutes ago and give me 4 or 5 seconds to think about it. I can get the answer correct every single time. Because I think about it and use some logic. If I add them together, then the bottom becomes bigger. As the bottom becomes bigger, FD becomes smaller. And as the apparent frequency becomes smaller, then I picture the fire truck moving away. Therefore, it's positive when the objects are moving away from each other. Now, when's it going to be negative? Well, stands to reason that when they're moving towards each other, it's going to be negative. Think about that. If I make that negative and I subtract those two, VW minus VS, what do I end up with? A smaller number or a bigger number? Smaller number. And if I get a smaller number as the denominator on the right-hand side, then FD becomes bigger, right? This is smaller, this is bigger. And if the Doppler frequency, the apparent frequency is bigger, then that means that the source must be moving towards me. Remember, picture the video. The fire truck is moving towards me. I hear a higher pitch. It's moving away from me. I hear a lower pitch. Yeah, Jacob?
What if the fire truck is moving towards you?
If the fire truck, that's a good question. If the fire truck is moving towards you and you're moving towards the fire truck, then there's a whole other mix thrown into this equation. There's something else up here that we haven't put in. So the equation that we use is assuming the observer is at rest. And that's not always going to be the case, right? But for us, it will be. We just simplify it a little bit because it's already a complicated enough equation, right? If we have to add something to the top because the source and the observer are both moving, then we got a plus or minus on the top and a plus or minus on the bottom. And if it's already confusing to have one plus or minus in there, you can imagine how confusing it gets to add another one. It's a good question, but we won't have to deal with that. Okay? Although it is conceivable someday, you go on in physics, you will have to deal with that, right? But you'll be a little bit better prepared for it then too. Yep. What does VW stand for? VW just stands for the speed of the wave, just as it does in the denominator there. So VW, no matter where it appears, is how fast the wave is moving. The speed of the sound, the speed of the light wave, whatever it is that is the wave, that's what that is. Does that make sense? Is that okay, Danny? All right. Okay, let's take a look at an example here, okay? This one is 8.4 on page 432. It says, a train is traveling at a speed of 30 meters per second. Its whistle generates a sound wave with a frequency of 224 hertz. So we get two numbers given to us already. There's a speed of 30.0 meters per second, and there's a frequency of 224 hertz. Now we have to take note of which V this is and which F this is. What V is this? Is this VW or VS? This is VS, the speed of the source, right? The speed of the source. The speed of the train that's producing this sound. It's actually It would actually be the speed of the train whistle, but of course it stands to reason that if the train is moving that fast, the whistle is too, right? Speed of the source. What F is this? Is this Fs or Fd? This is Fs. This is the frequency of the source, the actual frequency, Fs. You're standing beside the tracks as the train passes you with its whistle blowing. What change in frequency do you detect for the pitch of the whistle if the speed of sound is 330 meters per second? We're going to say the speed of the wave, or the speed of the sound, is 330 meters per second. How would you deal with this, by the way, if you were given a temperature instead of the speed of sound? Yep. Yeah, you just say V is equal to 331 plus 0.6 times t and find the speed of the wave, right? We have the speed of the wave here, so we don't need to do that. VW is 330 meters per second. What are we looking for? We're looking for the change in frequency. Let's get FD. That's not the change. That's the apparent frequency. But let's get it twice. Let's get the apparent frequency as it's coming towards me, and then as it's coming away from me, and then what am I going to do? Subtract them, right? We're looking for the difference in frequency, the change in frequency. So let's get both, then subtract them. So as it's coming towards us, moving towards us, we're going to say FD is equal to VW over VW plus, or is it minus? I forget. Hey, Jacob's saying it's minus. Let's just check that. If we make it minus Vs, then that number on the bottom is going to become smaller. And if that number becomes smaller, FD becomes bigger, right? And if that number becomes bigger, it stands to reason that it's moving towards us, so Jacob was correct. VW over VW minus Vs times Fs. What do we got here? 330 divided by 330 minus 30 times the frequency of the source, which is 224. Let's figure that out on our calculator here. Let's say 330 minus 30. Let's say 300 divided by that. Sorry, that should have been 330 divided by that, right? 330 divided by 300. And then let's multiply that by 224. We get a value of 246.4. I'm not going to round that. How come? Not a final answer, right? 246.4. Now, the actual frequency was 224. The apparent frequency is 246. Is that a reasonable number? Absolutely. It should be higher, right, because it's coming towards me. Now, when it's going away from me, I'm going to do almost the same thing, except the equation will have a slight modification to it. We're going to say FD this time is equal to VW over VW plus Vs times Fs. We're going to say 330 meters per second over 330 plus 30 times 224. What does that give me? Let's figure it out. 330 plus 30 is 360. 330 divided by 360 gives me a value of 0.916 times 224 gives me a value of 205.333. The actual frequency was 224. The apparent frequency is 205. Is that reasonable? Yeah, as it's going away from us, we should expect an apparent frequency that's lower than the actual frequency. Go ahead.
Isn't the apparent frequency gradually changing?
No, it's not a gradual change. It's as it's coming towards us, here's the frequency. As it's going away from us, here's the frequency. Now, we perceive that as a change. We perceive a change there because we can't detect that instantaneous change. Just like we have this visual persistence where we perceive motion when we look at photographs, right? You look at a movie, what are you really watching? 30 frames per second or 60 frames per second of photographs, right? So we have this visual perception of motion when there's not really motion there. Just the same as we'd have this visual perception of a change of a more gradual change in frequency when really it's instantaneous. All right, so what are we going to do here now? We're almost done. We're going to subtract them, right? we're going to say the change in frequency is simply going to be 246.4 minus 205.3. What does that give me? 41.1 hertz. So the apparent change in frequency is 41.1 hertz, or technically, I guess you should say negative 41 because we decreased by 41, but good enough, good enough. Yep, not yet. Does that make sense? You guys okay with that? All right, I'm going to hand back your unit assignments for just a second, and I'm going to ask you to take a look at, I believe it was question number 7 on your unit assignment that you couldn't do until now. I believe it involves a temperature as well, so remember you're going to use that 331 plus 0.6 times the temperature in the mix there. If you have any questions about that, just make sure you ask them. Now's a perfect time to do that, right? And I'll help you with that. I'm not going to do the question for you, but I'll help you with that. When you're done that, in about 5 minutes, I'm going to collect it back in. We'll mark those. We'll get those back to you tomorrow. Go over them in preparation for our unit test on Thursday.